Vienna University of Technology. Currently, he's doing his PhD at EPFL in Switzerland in the field of distributed systems with a focus on Byzantine fault tolerance. Let's hear from him.
Thank you very much for the introduction. So, good afternoon from me. As you heard, my name is Matej Pavlovic. I'm a PhD student at EPFL, and I'll be talking about one specific point of view on blockchains, more from the distributed systems perspective. This is joint work with Adi Serebinsky, also a PhD student from EPFL. He's sitting in the back of the room, and we were working on this project together. We were supervised by Rashid Gerawi, our advisor in the distributed programming laboratory. All right, so blockchain is very popular. Everybody's talking about it. It's just everywhere, and people are trying to use blockchain basically everywhere now. Any technology that can be seen as some online service, people have been thinking of how can we use blockchain to improve that or to make it somehow better. And there's many good reasons for that. The blockchain technology is very interesting from many points of view, also from the technological perspective itself, but also there's a very interesting philosophy behind it too. Otherwise, we would not be sitting here today. But what is blockchain? What exactly is that? Well, there's many things one could say. Blockchain, obviously, it's a chain of blocks, but it doesn't really help us too much. Blockchain can be seen as a data structure, as an abstraction in distributed computing. Blockchain is a distributed ledger. It's even a computer system sometimes. It's a consensus algorithm. It's a way of stopping wars and curing cancer and ending poverty and everything. It's just a revolution. It's revolutionizing the world, right? And it's great that people talk that much about that. And any of these things, in some context, is true. Well, maybe except for the last one. We will see. So, in this talk, I will try to shed a bit of light on understanding how we can deal with this. There are many paths to obtaining a blockchain. Everything started to be very popular in the late 2000s, where the famous Nakamoto Bitcoin was published and implemented. And since then, many other variants of blockchains emerged. Hundreds of them only on very same principles as Bitcoin, but there are also other approaches. And note that I included some other things that are even much older than Bitcoin, like 20 years older, like PBFT, stands for Practical Byzantine Fault Tolerance. And I included this because, in fact, it also can be used to implement the blockchain in a more traditional way. And Ziziba, which is just some optimization or sort of better version of PBFT, which turned out actually not to work as well as we have seen recently, but that's another story. All right. So there are many questions that we can ask ourselves, like which of these protocols is better, which is faster, which is more secure, how robust are these protocols, and I will try to propose you yet another way of looking at this, especially on the robustness question, by my talk today. And it's very hard to give a general answer on this. The answer actually is quite obvious. The answer is it depends, as it always depends. But on what does it depend? How does it depend on these things? We will try to have a closer look on this. So in the rest of my talk, first I will give a brief recap on what consensus is and how it is distributed, how it is related to ledgers and replicated state machines. Then I will propose a unifying scheme of how most of these protocols work in order to be able to compare them. And I will describe 4 very simple steps that most of these protocols follow. Then, in the end, I will present what we call indulgence of state machine replication algorithms, which basically is a view, some view of how the guarantees that these protocols offer are dependent on the assumptions the systems need to have. All right, so let's talk quickly about consensus ledgers and state machine replication. The consensus problem in distributed systems is the problem of multiple nodes agreeing on a single value, which turns out to be pretty hard. What we mean exactly by consensus is a protocol that has the following properties. The first property is safety. Safety says that first, no two nodes must choose a different value. And also that if a value is chosen, this value must have been proposed by at least one of the nodes that participate. Now, the second fundamental property, which we call liveness, is that some progress must be made. That means each node eventually must choose a value. No, we should not be just sitting there and doing nothing, trivially satisfying safety too. All right, this is a fundamental problem of computers, of distributed computing. Most of you probably know it anyway, and it's a very hard problem to solve. Now, how does it connect to ledgers? Well, what is a ledger first? A ledger is an ordered sequence of transactions. And if I was the only one to maintain such a ledger, things would be quite easy. Because I would just append one transaction after the other, and I would tell you what's in the ledger. But if we all collectively had to manage such a ledger, for example, because you don't trust me to tell you the right thing, or to not lie to you about the transactions in the ledger, things start getting much more complicated. Especially because we would need to agree on the contents of the ledger. And this is why we need consensus. We need to agree on what is the end transaction of the ledger. This is at the very fundament of any blockchain protocol. This is the hard problem we need to solve. But looking at it like this, it smells like a problem that we already know and we've studied a lot, which is state machine replication. Just imagine that a transaction is not just a transaction, but any arbitrary operation on some state machine, and we get basically state machine replication. Here, the clients submit operations to replicas that collectively distributedly execute the service, and these replicas, they would need to agree using some method of solving consensus what the order of the transactions will be, and then we'll respond to the client. So a distributed ledger is actually a state machine replication scheme. And this has been studied a lot for decades. Now, the properties that we want to have in a replicated state machine, again expressed in terms of safety and liveness, are roughly these. Nodes must observe the same sequence of operations. That's safety. So all the operations must be executed in the same order by all replicas. And liveness, again, means some progress must be made, which means if a client issues an operation, all correct replicas should eventually execute it. Sounds very simple, but it's quite hard to do. Now, there's plenty of algorithms that try to do this, all ones are new ones, but do all these algorithms satisfy these properties? Or even more importantly, under what assumptions do these algorithms satisfy the properties? And here, as the title of the talk says, here the details come in. That can be very tricky to distinguish and to resolve. Now, in order to answer these questions, what we do is we present a framework for comparing these protocols in a very, very simple unifying scheme for state machine replication algorithms, under which blockchain protocols definitely fall. And we try to use this framework to point out the differences between the algorithms. And the adversary lies in the details, and the details are how the protocols implement different parts of the scheme we propose. All right. So what is our general scheme? The framework that we propose, that we believe on some high level most of the blockchain and state machine replication algorithms follow, is very simple. It can seem almost trivial, and we decompose state machine replication algorithm like this. First, some client needs to issue a transaction. That's quite simple, and there's usually not much trouble in this. The client just finds a way to announce that it wants some operation to be executed. Now, the other steps are more interesting, because this is where it starts differentiating a lot. The leader election step is in one way or the other present in most of the algorithms, although on a very abstract level. Most of the algorithms rely on some kind of centralized decision that is then spread to the others. What we mean, okay, the third step is committing on what the leader decides to do. Now here, the decision of the leader needs to be somehow spread to the other replicas, and the other replicas need to somehow adopt or not adopt what the leader is proposing. And the fourth step is reconciliation of potential conflicts. Now, I put it in parentheses because some protocols inherently don't need it, and some protocols do. Actually, some protocols, the crux of all the protocol lies in the fourth step. For example, in Bitcoin, this is a very, very important step that many things rely on. All right, so just not to be too abstract, I picked two protocols to demonstrate how this scheme can be implemented very differently. And I tried to choose two quite different protocols. One is the almost canonic practical Byzantine fault tolerance state machine replication protocol that was proposed 20 years ago and is still used as the basis of comparison for many other state machine replication protocols. And Bitcoin, that I don't have to say too much about that here, I guess. All right, so let's look at the first step. In the first step, there actually is already a difference, because in PBFT, the client just needs to send an operation if it wants to be executed to the leader. This is quite straightforward, and the client usually even knows who the leader is and can send the operation just there. And if the node happens not to be the leader, it's rather easy to forward the operation to the leader, because this is a known thing. In Bitcoin, it's already different, because Bitcoin doesn't have such an explicit leader, especially not at the time when an operation, which means a transaction, is issued by client. So the client somehow needs to spread this operation among many miners and hope that these will include it in the next block. All right, the leader election is already much more interesting. Leader election, in an abstract sense, does exist also in Bitcoin, I would argue. There's a difference between Bitcoin and PBFT. In PBFT, the leader is determined using a current view number, which is inherent to the protocol, and the node membership, which is required to be known by all the replicas. And this normally doesn't really change too much, unless the leader is faulty, or is lying, or is off. This doesn't really change. In Bitcoin, nobody even knows who the leader is. It's not even so clear that there is a leader. So what we consider to be a leader in Bitcoin is the first node that is able to solve a computation problem. So the first node that can solve a proof of work, that can present to others that it did a lot of computation, can be considered from our point of view the leader, because this node is allowed to serialize a block of transactions. All right. Now the commitment phase. It's also very different. In PBFT, it's a rather complicated three-phase quorum gathering protocol, and most of the PBFT algorithm actually lies in this three-phase commit protocol. This protocol ensures that before the replicas commit to something, most of the replicas actually agree, and the result will be irreversible. In Bitcoin, this is almost trivial. If I receive a block that has a valid proof of work, I accept it. I can verify. It is much simpler than in PBFT, but it doesn't really give me so nice guarantees as PBFT gives me. In this sense, the fourth phase is somehow the inverse. In PBFT, it's trivially pretty much non-existent. In PBFT gives us what sometimes we call consensus finality, where once a decision is made, there's no way to revert it. In Bitcoin, there can be conflicts, and that's why this fourth phase is very important in Bitcoin, although it doesn't exist in BBFT. A conflict here, which means a fork for Bitcoin, is resolved by considering only one block of the fork, or only one branch of the fork for future transactions, and only this helps us to reconcile conflicts. All right, so these are two different protocols. They solve basically the same problem with two very different approaches. Now, do they offer us the same guarantees? Well, obviously not. Otherwise, I wouldn't have anything to talk about here. So, what are the differences? What are the details that make them different? Well, some quite important details I already disclosed to you, and now let's have a look on how these details manifest in terms of guarantees these protocols provide us, because these are actually quite different. To this end, we introduce the indulgence of state machine replication algorithms, which is a rather fuzzy term, but potentially interesting in the way we are looking at state machine replication protocols. What we mean by that is how the safety guarantees provided by these protocols depend on the assumptions we need to make on the system in order to make it work. Specifically, assumptions on the adversary. Now, what do we mean by assumptions on the adversary? Well, what is the adversary? The adversary we consider to be some abstract entity that controls different parts of the system, and of course, if we allow the adversary to control everything, then there's not much we can do. So we always need to restrict the adversary somehow. Now, we propose to distinguish two different kinds of assumptions, which will determine the indulgence of our protocol, of many protocols. Now, first, we consider synchrony assumptions. Synchrony assumptions basically say how fast the honest nodes can perform computation and communication. This doesn't really tell us anything about how the adversary can be malicious. This is just how the honest nodes deal with time and how on time they are with computing and communicating. This is a rather broad set of assumptions. For example, even an assumption that says that network partitions only last a bounded amount of time is a synchrony assumption. Or we can assume that there can be DOS attacks, but they will never last forever or something like this. These are all synchronous assumptions. Then the other kind of assumptions is what we call behavior assumptions. These are basically assumptions on how malicious nodes can be and how many malicious nodes we can have, how many malicious identities we can tolerate such that the system still works. This is very important, for example, for dealing with Sybil attacks, where potentially almost all of the nodes can be malicious, and we need to deal with these situations. Okay, so to get back to our examples of PBFT and Bitcoin, it actually turns out that they belong to quite different classes based on our indulgence. So one class that we propose is so-called A-indulgent algorithms that preserve safety during asynchrony, which means the synchrony assumptions that these protocols make do not are either small or even none, and the protocols will still provide us safety, which means in terms of Bitcoin, no double spending, for example. The other kind of protocols is B-indulgent protocols, which on the other hand preserve safety despite a lot of malicious behavior in the system. Now, we don't necessarily claim that these are exclusive, as we will see later. But we think that this might be an interesting way of seeing protocols and maybe choosing them based on where we want to deploy them, what we want them to do, and how we're going to use them, and what we expect from them, and what we can guarantee as assumptions of the system. So PBFT is a typical A-indulgent protocol, while Bitcoin is a typical B-indulgent protocol. In PBFT, committing operations is ensured in the third step of our scheme, and safety is always ensured as long as the big enough quorum of the participants is honest. No synchronous assumptions whatsoever are required for safety here. That's why even if the system is asynchronous, safety is never broken. That's why PBFT is A-indulgent. It's asynchrony indulgent. However, PBFT is not really B-indulgent because 1/3 of identities being Byzantine breaks everything. On the other hand, Bitcoin is exactly the opposite. Bitcoin always commits everything that has a valid proof of work, and conflicts are resolved later. Now, this means it's not really asynchrony indulgent because it's vulnerable even to partitions, even if everybody is honest. If there's a partition in the network, then we can have double spending, even if we don't want to have. So it is, however, much more indulgent to malicious behavior because we can have many identities in the system, and if they don't possess enough computing power, they would still not be able to overthrow the protocol. All right, I'm slightly running out of time, so I'll go just quickly about other examples of protocols. For example, Bitcoin NG. That's another example of a B-indulgent protocol. It is different than Bitcoin, but then if we actually try to use our scheme and fit Bitcoin NG in this four-step scheme, it turns out that most of the steps are principally very similar or the same. So in this sense, it doesn't really differ too much, and it's also B-indulgent. Algorand, a much newer thing, is already more interesting, and it's somewhere between PBFT and Bitcoin concerning the indulgence. I will not go into details here. It's slightly more detailed in the paper that you can check out afterwards. And my last example is Bitcoin, which is also a very interesting hybrid between PBFT and Bitcoin. And in this sense, it's also a hybrid between A-indulgent and B-indulgent algorithms. It's a combination of BBFT and Bitcoin. For the leader election, it uses BBFT. It uses Bitcoin, and BBFT is executed somehow on top of it. So it tries to pick the best of B indulgence and A indulgence. However, it has other drawbacks. For example, it might trade in liveness, which is not really mentioned in what we consider A indulgent and B indulgent protocols. All right. To sum up my talk, I said that distributed ledgers are equivalent to consensus and state machine replication from a distributed system point of view, and that most protocols follow a very simple, very high-level four-step scheme that applies to how consensus and state machine replication is reached. And it's the details in how these protocols implement this scheme that make a potentially big difference in the guarantees the protocols provide. Based on how these steps are implemented, protocols can be seen as A-indulgent, which means asynchrony indulgent, that are safe despite of asynchrony, and B-indulgent, or behavior indulgent, which are safe despite many malicious nodes present in the system. Thank you for your attention, and if you have any questions, I'll be happy to answer them.
Is the concept of safety the same as acid without C? Does it mean isolation and durability in addition to atomicity?
The concept of safety in distributed systems is, I would dare say, much more abstract than that. In fact, in distributed systems, when we have some distributed abstraction, it is very often described in terms of safety properties and liveness properties, where safety property, each abstraction has various properties that basically define the abstraction. And the properties this abstraction has are either considered safety properties or liveness properties, where safety properties define what must never happen. For example, in the consensus, the agreement property, meaning each node outputs the same value, is a safety property because it can be easily checked that when it's broken. So if I have two nodes and they decide a different value, I see, oh, that breaks the property. It's basically saying what must never happen. And if that happens, I can see that. That's a safety property. Or a value that hasn't been proposed is chosen, that's violation of a safety property. Liveness properties, on the other hand, are mostly progress related.
If you're going to talk about liveness, can you compare it to CAP here?
Okay, the CAPs here.
Is this a trade-off between consistency and availability in the process of network partition?
In some sense, yes. In some sense, yes. So either you have progress or you have safety. Yes.
Thank you.
So, I had a question about your likeness definition. If you look particularly use like
This one? Or the liveness of the consensus?
Yeah, exactly.
Yes.
So, I was just thinking that this doesn't seem to guarantee that consensus is reached, right? It only guarantees that people proposing the code, but not necessarily that eventually they agree on the code. Isn't that like this?
But you need both of them. You need safety on liveness to have consensus. If you have only one property, you don't have consensus.
Actually, reaching a single only safety or only liveness is always trivial. Always. Because if you do nothing ever, then safety is reached.
No, liveness involves that nodes make decisions and they are not blocking the system.
Yes.
If you would block the system, you could not reach consensus. If you would have a quorum of nodes not doing the job.
The liveness ensures that you will achieve that.
Something.
Yes.
You will end up somewhere.
Basically,
When
liveness
everybody
always,
can say I'm done.
Yeah.
Yes.
And at that point, we agree,
yeah.
right?
Basically, liveness says you have to do something, and safety says what you do must be correct.
Did you scale Casper? Casper, the proof of stake from the future proof of stake of Ethereum.
The future proof of stake.
Are you asking if you compared it?
Yes, you could. Did you?
We didn't consider it in our
It
conference.
would be interesting because.
Yeah, we invite everybody to try to fit other protocols in our
Because
scheme.
it's supposed to be the next consensus mechanism of Ethereum on its proof of stake.
Yeah, well, it would be definitely interesting to do that.
And it most probably something which is a mix between PBFT on pseudo proof of work and so on. So it
Yes.
would be interesting.
Yes, definitely it would be. I mean, for most of the protocols, it would be interesting to do. We try to just pinpoint some to showcase that something can be in the middle. That doesn't have to be at the extremes.
So I want to mention that I have seen it's a PowerPoint presentation from a person in IBM who's been escaping a function at it, but that does do this, where the rows are different consensus schemes, including proof of work, proof of stake, basically fault tolerance, SID,
Markov
and so on. No, I'll try to make it up. But then the rows are, what type of guarantees does it give you for Byzantine fault tolerance, so many of the things that you described in your axes, I feel like I've seen in that type of table. So
Yes.
at least it's a parallel effort to it.
Yes, I think I might be at least slightly familiar with that, because I also remember such a table. There is, yes, there's like different guarantees the protocols can give you. What we try to do is to see how these guarantees depend on the decisions of implementing these steps of our four-scheme generalization.
Is another point of distinguishing the permission versus permissionless setting? Could that fit in your authorization?
I think the permission versus permissionless.
Like Bitcoin is permissionless and PBFT is permission, right?
Well, it depends on how exactly we define these things. Because we had a lot of discussion about this, even in the context of this paper.
Okay.
Like, what is permission and what is permissionless?
Okay.
Because if you say, or how exactly to regard it? Because you can have or what is it a statement about? It is a statement about the environment, or about the protocol itself, or what exactly do you mean?
So the protocol, to start, it requires a fixed number of parties with known identities, right? So
Yes.
this is the permission setting, and then you have a protocol that needs this as a requirement to start, right? So,
Yes.
So and then the permission is that there's nobody, there's
Yes.
no such
Well, yes.
so
This
is
is.
that a distinction or not? I mean,
It is still rather fuzzy in our opinion, because you can have a permissionless setting where everybody can join, for example, right? Anybody in Bitcoin, you just generate a key pair, you can join the protocol in some sense.
This permissionless.
That's
Yes,
permissionless.
that's permissionless.
Yes, yes.
But you can make PBFT also permissionless in the sense that you implement reconfiguration and you just allow anybody to join the system, right?
Even
Now,
after you
It would be less
start.
secure because then you
Even
would
after
be
you start.
going to see that very
Exactly,
easily.
and PBFT would be prone to simple attacks like this. Now we can now speculate. Okay, is permissionless that it actually could resist this, or is it a permissionless setting that PBFT can go but doesn't work in that setting? And
So,
I think the question is more which protocol to be used in a permission or permissionless, and it will depend on your context.
Yeah.
As you were
So
saying,
in general,
it depends.
yeah. In general, I would say yes. The answer is
So
always
is
it
it your
depends.
point that PBFT can be made permissionless as long as the quorum assumption is maintained as people are joining?
I would say yes, but
Okay.
this assumption is almost impossible to guarantee
Yeah, but
in a permissionless setting.
theoretically, if that was the case, you could.
Yes, I would say so. And then here, if we have a permissionless setting, and we're choosing a protocol, then probably we would like to choose a B indulgent protocol.
Okay.
This is where our work hopefully could be somehow useful.
All right, thank you.
Thank you very much.